Yeah, very good evening. Uh, so the outline for this lecture 9, we'll conclude subgradient calculus and then look at optimality conditions in terms of subgradient. Obviously, largely for convex functions. We'll also look at some principles for optimization and so on, and also motivate algorithms that will also form the foundation for discussing convergence criteria, Lipschitz continuity, and so on. So that's how that flow will be. Let's see how much we can cover for today. So as an outline, where are we right now? We concluded first and second order conditions of convexity. We discussed some of the basic subgradient calculus conditions. Right, this is almost done, and that's the stage for convex optimization problems and basic optimality conditions and so on, and then Lipschitz property. Okay, so I had left you with a homework problem. And the homework problem was kind of motivated by this so-called holders equality. So recall that we had discussed the one norm and its subdifferential, right? So there were two ways we were trying to approach the one norm. The one was the subdifferential of one norm derived from first principles. But what was first principles? That's as max of S transpose X with S as n-dimensional vector of minus ones and plus ones. Right, this is what we had done. So we derived the subdifferential. What was this? Nothing but. Okay, so that's what you're supposed to recap, right? We had some expression here, and we set off with the holders inequality. This, of course, one perspective of holders inequality is generalization of the Cauchy-Schwarz inequality, which was basically defining the P norm of X as max or supremum. Actually, you can consider it supremum or Z with Q norm upper bounded by 1 of Z transpose X. With the understanding that P and Q, their reciprocals sum to 1. Recap all this, right? So the holders inequality was our first exposure to duality, right? We can define the P norm also P greater than 1, let's say, right? As summation absolute value of X size raised to P, the whole raised to 1 by P. Right, so we got two views of the P norm of X. One by construction, one by kind of negation. That's what I said. This inequality is like saying max over mini Z transpose X. It's like chiseling away. That's a dual view. The primal view was by construction. Similarly, we got the subdifferential of one norm of X by construction. What did I leave you as homework? Well, I said Can you now derive the subdifferential of 1 norm of x using the dual definition? But of course, I gave you a little bit more ammunition to get there. What was the ammunition? Uh, yeah. Okay. So sorry. This is the subgradient. Sorry. This is the expression we had derived. This is a convex hull of all the S such that S is in S star, where S star is all the S star is -1 plus 1 raised to n, such that 1 norm of x equals S transpose x. Basically, all the S is that the sum of absolute values of the components of x correspond to Si, right? So if you want to write this down, basically saying sum of absolute values of the xi's should be sum of Si times xi. It's clear? So I'm just recapping everything that was required to get to. Okay. So now we got from the dual. So this was primal, but from the dual definition of the one norm of p norms in general, we derived the we showed um, an interesting characterization of the subdifferential. What was that characterization? This led to the subdifferential of the p norm of x. This expression that you see here is all the y's such that the q norm of y is less than or equal to 1, and the dot product of y with x coincides with the max across all the z such that z transpose x is such that norm of q norm of z is less than or equal to 1. This expression. So what is this? This is y such that the q norm of y is less than or equal to 1, and y transpose x is max over the z q norm less than or equal to 1 of z transpose x. Now, this is where we left off. And to make a little bit more sense, right? So you might find it a bit esoteric. Sorry. Oh, fan. Switch. I think it's behind these projectors. So there could be one more behind the screens. Okay. So now we wanted to get a bit more grounded in this dual description. And what did we say? Can we kind of derive the subdifferential of x based on this dual definition? Okay, so what are we doing here? Saying that based on this, can I again revisit the subdifferential of the one norm of x? So any attempts? Any good luck? Can it become simpler? We expect it to be the same, obviously. But can you get a more concrete expression? Just look at this, right? So what happens if you set p equals 1? P equals 1 would mean q equals p you set to 1, Q should tend to infinity, right? So P equals 1 implies Q tends to infinity. Okay, so so this should basically mean, so I'm going to write an S instead of Y here, an S, so that it just looks like that is, such that the infinity norm of S, well, less than equal to 1. Generally, when you say less than equal to 1, why would you leave any slackness? You'll allow it to be equal to 1, generally. And S transpose X equals again max of the infinity norm of Z less than equal to 1 of Z transpose X. Okay. Can you simplify this expression further? I just substituted it, right? And you say Z infinity norm less than equal to 1, what will it amount to? Each entry plus 1. Each entry is allowed to be less than equal to 1 in absolute value, right? It could be at most plus 1 or at least minus 1. Now, if I'm allowing this Z transpose Z X and I want the max value, so it's but natural that I'll let Z the max be plus 1 or minus 1. Okay. We'll argue a little intuitively, but you can work this out. This is not so difficult, right? So this is pretty much like saying that S transpose X is max over Z minus 1 comma plus 1 raised to n of Z transpose X. The same expression, right? It's basically a vector of plus 1s and minus 1s. Can this be further simplified? All this is fine. It will be further simplified. Sum of absolute values of X. Okay. This should be the sum of absolute values of X. Makes sense. And what else? So I still want the characterization of S. So this is fine. We seem to be making good progress. Okay. But can I make it even more concrete? So can I say that whenever Xi has positive sign, Si, I make it to be positive. When Si is negative, I make S to be negative, minus 1. So can I say that this is nothing but S equals or Si, S1, blah, blah, S2, Si, Sn, such that Si equals minus 1 if Xi less than 0. Si is plus 1 if Xi is greater than 0. What can Si be if Xi equal to 0? Anything in the closed interval minus 1 to plus 1 if Xi is equal to 0. Why? Because I lose nothing, right? By making it anything between this in this interval. Okay, so this is the final expression. Obviously, the way you write minus 1 plus 1 could also be as a convex hull. So minus 1 to plus 1 is what? A convex, this interval, sorry, the closed interval, minus 1 to plus 1 is a convex hull of minus 1 and plus 1. Okay, so this expression can be written more fancifully as the convex hull of minus 1 and minus 1 and plus 1. Actually, yeah, I should just say let's of the set. So write it differently. Convex hull of the set minus 1 comma plus. Okay, so you see that the primal and the dual give you the same final expression, but the paths are somewhat different. So this is our second exposure to duality. One was duality in terms of the definition of norm. Now for a specific one norm is subdifferential, we got it from both the primal and the dual definitions, right? Is this clear? So this, the final expression is here. If S star is in minus 1 to plus 1 raised to n, be the set of S such that for each S, the value of X transpose S is the same max value, right? This is what he had showed earlier. This is the same as a slightly more procedural. This is slightly more procedural, right? You've just said you can get SI as minus 1 plus 1, blah, blah, blah. Or a convex hull of minus 1 to plus 1. It's exactly the same. Any questions on this? This is important, okay? Make sure you understand this one norm example really well. Any questions? It is very critical. If you get this, you should be able to get many other subdifferential expressions. So there was one question in the last class. Somebody asked me after the class, what is this notion of closure? So remember I talked about the closure of this convex hull when we were looking at Supremum. So in case we were looking at Supremum of S transpose, or Supremum of Fi, right? Whatever. So recap, if you had F is Supremum over S in capital S of F is X, right? Then what was the subdifferential of F of X? It was the closure, it was the, sorry, it was a closure of the CL, okay, CL, meant CL. Closure of the convex hull of the union over S in S star, right? The support set. S star is like the support set where all the, where whichever functions have the max, right? So of the subdifferential of F of X, obviously at X. So remember, this is what we had discussed. This is a generalization of the convex hull, right? And this S star is the support set. So there are some questions on what is really closure. So I'm not going to define or rather write too much to define, but I'll refer you to my notes from last year. I mean, not last year, sorry. Notes from the convex optimization offering of this course. So there's some topological concepts we talk about here. So okay. I hope all of you understand what an interior point is. Okay, before that. Yeah, this is the key thing. A point X is called an interior point of a set S if you can draw a ball, an open ball, right, around the point X that lies within the S. I hope you know what is an open ball, right? So I won't get into that. You want an open ball, right? So, and it's a ball. We're not talking about a set. So this is a ball. B x epsilon. So assume that you have Euclidean norm at your disposal. So under the Euclidean norm, there must be a ball, radius epsilon. Such that it lies an open ball, which means the boundary is not included. That's a subset of S. For every x, there must exist some epsilon. So if you're very close to the so-called boundary, which may not be part of which will not be part of the open ball of the set if it's open, right? But if as you get close enough, the epsilon may shrink, but there will always exist an epsilon. And the interior of a set, on the other hand, is basically the points lying in the interior, right? Point x is an interior point if there is an exists an epsilon, and the interior set of all those, right? Uh, and what about boundary? What is the boundary of the set? The ball will have with both F and S. So for every a boundary point, let's say this is a boundary here, right? Or boundary of this table. So any ball I take here will have some part within the table and some part outside the table. So this is the boundary. It doesn't take sides. Right? Now it's not necessary that the boundary is part of the set. Maybe my table is everything except the boundary. But still it has a boundary, right? Because if I put a point in the boundary, some part of the ball will foray into the so-called table, the table which has its interior. Right? Right. So the boundary of a set is exactly what we were saying, right? That all the points y says that there y says that for any epsilon. Here this for every epsilon. No matter which epsilon I take, not there exists an epsilon, but for every epsilon there will be some part of the ball will be outside, some part will be inside. And what's an open set? An open set is such that yeah, there exists an epsilon such that a ball x comma epsilon is a proper subset of S, right? For every x. So no matter which x I take, that's what I began with, right? I should be able to find a ball, some epsilon, which is lying completely inside that set. What is a closed set? Set at all. Yeah. So one way is saying that it has all its boundary points. The other way is to say its complement is the complement. A set is closed when its complement is open. Right? So closed set is closed when boundary is contained in S, right? Or it's I've given both definitions. When S complement is an open set. And then now we come to the final. This is the closure of a set. What is the closure? Yeah. So the S may not be open. Sorry, S may not be closed. It may be open. But closure will always be closed. Right? It's basically all the points Y, which includes points in S and points on the boundary, such that if you take any epsilon greater than 0, then the ball centered at that point, which may be in the set or in its boundary, must have a non-trivial intersection with the S. So imagine the S is, let's take example, the S is the interior of this table, right? So closure of this table, as you would expect, is the entire table, including its boundary. Why? Because if I take any point in the closure, the Y, sorry, yeah, all the Y. So Y, any point in the closure, if I take any epsilon ball around that point Y, then it so happens that it has some non-zero intersection with the S, even though the S is the interior. S may be the interior, S may be the closure itself. In this case, S was the interior of this table. The closure is the entire table. And any point I take, including the boundary, for all epsilon, there's a non-trivial intersection of that ball y comma epsilon with the interior of the table. In this case, because interior of the table was RS. This is clear? Okay. So I think this somebody had asked for the definition, so I just brought it up. Okay, with that, we move to a very interesting expression. A simplified form of what we call the lasso. So lasso is basically the least squares regression loss function with a one norm regularizer. Right here. This one. So one norm regularizer on X. So what are the subgradients of fx? Can we try and derive? Let's try and derive the subgradients of fx. It's a simplified form of lasso, as I said. Why is it simplified? I just said 1/2 y minus x norm square. Isn't this simplified? How is it simplified? Huh? Yeah, there's no A, there's no matrix A, right? There's no matrix A. Ax simplified to x, as you see in this blue part. Okay, so if I have to compute its, I've now just done the following. Okay, I have just taken all the expressions so far. Let me erase this. This part I can erase. I'll retain the part in black there. Okay, have a look at it. I have kind of given you some initial lead so that you can derive the expression. Oh, sorry, I erased this. And so I've just taken the simplified expression. I've used x instead of w. Usually you use w for the weights. X is the parameters, w's. And I'm going to look at the subgradient for this part. What is the subgradient for the first part? 1/2 y minus x squared. Sorry? Yeah, x minus y. Actually, you can write y minus x as x minus y. That makes it easy. Y minus x norm square is x minus y norm square. This is x minus y. What is the second part? My goodness, this ink leaking like anything. What's the second part? Minus one. Right. I'll make it simple, right? S transpose X says that it is the same as summation over I of the absolute values of Xi. So basically, these are so that's what we had seen earlier. So this, or in other words, Si is plus 1 if Xi is greater than 0, Si is minus 1 if Xi is less than 0, and it's between minus 1 and plus 1 if otherwise. As otherwise means like Xi is 0. Okay. So you actually can write down the expression x minus y plus a vector of minus 1 plus 1 based on the signs of Xi. So yeah, I mean, instead of doing all that, I just said x minus y plus lambda s. Lambda s is Si has Si sin Xi. So exactly what I wrote on the board is written there on the slide. But we'll put this to good use today. So anything else? So we have already shown an illustration, some subgradient calculus. So we've dealt with uh, max and so subgradient calculus, right? Max and Suprema. I'm not even talking about affine transforms and all that. Those are simple, right? Maybe we'll bring it up, but we are going to look at the non-trivial ones. The second one is the composition. So now, this is what we saw was an example of max. For composition, remember our favorite f of x is h of g of x. Right. So what were the two combinations we always talked about? One is h is convex and non-decreasing, g is convex. Is that correct? What was the other one? Or h is convex and non-increasing and g is convex. Right? One of these two cases. Okay, so now I have now talked about the more generic case where okay, I use PQ. So let me be consistent. I use PQ there. Okay, so you can do the same thing with each argument. Qi is convex, P is convex and non-decreasing in each argument, or Qi is concave in each argument. And P is convex and non-increasing in each argument. Of course, Qi is just one argument. I don't have to say in each argument for Qi's, only for P's. Sorry? Where is domain of H? Yeah, I meant domain of. No. This is FF. No, I just ignore this. Okay, I didn't know. I think I made. Oh no, I just said QX is infinity for all x not in the domain of F. Actually, just keep it to be domain of Q. Okay. QX is infinity if it's not in its domain. Okay, so let me just treat this to be Q. Where I got this H from? So this is domain of Q has come out too small, but yeah. Okay. Now the main question is, how do I derive its subdifferential? What will I need to do to get the subdifferential? Let's see the different color. How will I decompose a subdifferential? This is a big thing, and the compositions are quite useful. Okay? Any thoughts? Yeah, chain rule, but how? So if you had to derive gradients or just derivatives, what would you do? What's the derivative of P of Q of X? P dash QX into Q dash, right? So P dash evaluated at QX into Q dash. Okay, understand that difference. So let's take the partial derivatives. df. This is a partial derivative. Okay, don't confuse this with subdifferential. So I read it differently. So you understand this notation? It's a partial derivative of P with respect to X evaluated at QX. We won't call it Y, doesn't matter. Right? The whole thing should be evaluated. So just to avoid confusion, it doesn't matter. You should just call it Y or Z or whatever. And the partial derivative of Q with respect to Z evaluated at X. So how do you think now we will realize a subdifferential for compositions?
Differential of P evaluated at 2x.
Subdifferential of P. Huh?
Partition.
So would you have some products? You're pretty much there. I mean, it's not far from. So here are some examples, right? I'm just recalling exp of qx is convex if q is convex. So summation of log qi x is concave or minus of s is convex if qi's are convex and okay. So let's look at. So we'll look at subgradients for the first case. Okay, there are two cases. We'll only look at this case. We'll leave the second case as homework. It's not very difficult. So for now, let's fully focus on the first case. So pretty much what you said, right? Now we're just generalizing what the part we have written on the board in green to a vector. And the moment you say vector, you'll have some dot products. So what you have in the form of dot product are P. So actually, before we do that, I've just recalled what those definition of subgradient is. So what's the definition of subgradient? P at Q1 to Qk of y should be greater than equal to the P of Q1 x plus the subgradient of Q1 rather. Subgradient of Q1, you see this notation. Let me write this down. This subgradient of, so what are we dealing with? Let's identify this. So you're looking at P of Q1, Q1x, QKX. Okay, and for each of these, I have subgradients. So I have the subdifferential of QKX, and I'm going to pick one element from that and call it HQK in general. Okay, HQ1 is an element of the subdifferential of Q1x. The second thing we'll look at, or we need to assume the existence is a subdifferential of P, or a subgradient of P from the subdifferential. Okay, so I have not shown that in the expression here, but that will come very soon. So what have I done? I have kind of now written down one basic step at a time to show, well, there are the existence of a subdifferential of a subgradient for the overall function. So I use the subgradients of the constituents to construct the subgradient of the overall function. But the spirit is going to be very similar to this. Okay. So my first step is, so I won't write everything on the board. The first step, what have I done? I just applied the fact that P is non-decreasing each argument. Okay, so because P is non-decreasing each argument, so P of Q1y, blah, 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 QKY is greater than equal to P of Q1x plus some HQ1 transpose y minus x dot 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 QKX plus HQK transpose y minus x. Why? Because these are subgradients. If you want to write down the inequality. So what does it mean to say? That these are subgradients. What do you mean by subgradient? For Qi, y is Qi is greater than equal to Qix plus HQi transpose y minus x. So Qi's have this inequality, and our P. So this is Qi, right? This is for Qi, and P's are non-decreasing, right? So the first one in green is by definition of subgradients Qi, and the second fact, since P is non-decreasing, sorry, in each argument, right? If I now just slap this inequality everywhere, right? I get P of Q1y, Q2y, blah, 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 QKy is greater than equal to, why? Because each argument is greater than equal to the other argument. The P on these arguments is greater than equal to P of the right hand side. So this is LHS and what I'm going to write here is the RHS. P of Q1x plus HQ1 transpose y minus x, comma, Q2x plus HQ2 transpose y minus x, comma, HQ QKX plus HQK transpose, sorry, HQK transpose. This is clear. Now what do you do next? Okay, now the rest is for you to solve. I've gone so far. My goal is to get the subdifferential for F. So how do I now compose a subdifferential for F? What have I not assumed so far? I assume that Q's are convex, so they must have, right? Each Qi is convex. Qi convex implies HQi exists. What have I not used so far? I have not used the fact that P also has a HP. There's an HP as well. How do I plug in HP? Yes. On this inequality, I need to do something more and get an HP in as well. So plus on? P on this. Sorry? You're saying I can just add one more.
Yes, I HP transpose is no vector. If you talk about that, H transpose those elements are.
But how can I add something to the right hand side and still preserve the inequality? So don't jump, right? Be a little careful. The first thing you should say is, well, I know that Px greater than or equal to or Py greater than or equal to Px plus HP transpose y1. This is what I know. Now, can I do something here? Can I take one more inequality down? That will be the key. Instead of just saying I'll add something to the right hand side, I'll say this, the one you see here, P of this argument will be greater than or equal to P of, so what is this argument? So look at this argument, right? It's Q1x plus HQ1 transpose y minus x. So what will be, so what can I do? I'll take P of Q1x comma P2, Q2x blah 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 plus H, yes, this part, right? All these are dot products, scalars. These are scalars.
So we make
You could arrange them into a vector and right. So you're getting the spirit, right? It's just extracting out the second components and factoring in the HP along with those. So again, in the interest of time, I'm not going to just, right? So I've written this here, exactly what you said. So this part, P of, so I've given it a name also. Just sometimes it's easier, right? You're seeing a lot of complexity there. Just give it a new name. P of Q1x, QKX, this entire Q1x to QKX, I've given it a new name, R. So P of R is greater than or equal to P of R plus the second part, right? This part, I've given it a name W. So what have I done? I've just given this entire thing a name R. So this is all part of R. And the second components, I've given them a name W. Sorry? Y. I use X. So you're saying the slide. Well, I think
right hand side and left hand side are X.
Oh yeah, you're on the slide. This should have been Y. You're right. You're right. On the slide, I'll make a I'll make this correction. On the, this is Q1 of Y, Q2 of Y, QK of Y. Thanks. Right. Okay, so um, after this, what do I do? Since P is convex and it has also subgradients, P of R plus W is greater than or equal to P of R plus HP transpose RW. So let's just write it in terms of R. Okay. So I'm just going to reword this P of Y. It's like saying P of R plus W P of R plus HP transpose evaluated, of course, at R with W. This one.
R need another arithmetic bias.
Yeah, so R is basically a function. R is a function of Y and X. HQ1 Y minus X, HQ2 Y minus X. Also HQ1 transpose Y minus X, HQ2 transpose Y minus X, all stacked together. Right? That is what you see here. So only R, this part is R plus W. This is R and this is. Oh, okay. I think I should not be calling these R. Okay. I think the mistake is here. I'll just call this tilde. Is it okay now?
P of R. P of R integrates P of R.
Yes, P of R tilde. Actually, wait a second. I think this what I've written on the slide is correct. Okay. This I'm just talking about the non-decreasing nature in each argument. This is just the previous part. This is a new part. Okay. So yeah, what I've written on the slide is correct. This is just the previous part. Previous part, what did I say? Before I wrote all of this, I said, sorry, so this is correct one. Yeah. Not this. This was this part. Right?
That part is in the box.
Yeah. So I have now gone to the next step. So what I've written on the slide is correct. It's self-consistent.
On the left hand side, it should be Q1 of Y, Q2 of Y,
Yeah, sorry, it's still Y. You're right. It's still Y. Okay. So I got it. There's still a mistake. There's a Y here. Board is correct. Okay. So now all I need to do is bring in the HP transpose R into W. So what I've written on the board is correct. So this is just expanded here. Okay, so pay attention. P of Q1 X plus HQ1 transpose. This is evaluated at X. Qn transpose Y minus X. Blah blah blah. QKX plus HQK transpose Y minus X. This is exactly what I have second, right? This is greater than equal to. Now what have I done? I have applied this expression. P of R plus W is greater than equal to P of R plus HQ transpose RW. HP transpose RW. So I have brought the HP here. P of Q1X, QKX plus HP transpose the W. This is the W, right? This is the R, this is the W. Okay, it's just too laborious to write all that on board. I'm not going to write it. So what is my final? So let's just write down the final expression. I think that's all we want. One is composition of P of Q1 to K X for the case of convex, non-decreasing, and convex. Okay. So you see, I've got my new subgradient as using an HP from the subdifferential of P and an HQs from the subdifferentials of HQIs from the subdifferentials of QIs. Okay. And what is that new subdifferential? So tell me what is the new subdifferential? Yes, it is what? Subdifferential cannot have y and x both. Okay. Subdifferential has to be only with respect to x. Hmm. Now, HP transpose evaluated at R. A times W. So most often we don't do this. Okay, so this is HP transpose, or if you want to put R here, okay, that's better. H P, the whole transpose evaluated at R. Okay, so what is the final expression? This is it will be a vector, of course. HP is not a scalar. HP, you can also consider element wise. So how about the following? I mean, I'm just suggesting HP 1. Should I consider element wise? Okay. Should be okay. By the way, HQs are also HUIs are also vectors. Huh? HQIs are also vectors. Look at the dimensions of the two. What is the P is going from RK to R and Q is going from Rn to RK. The subdifferential of P composed with Q will be in should be in Rn, right? Because you're applying the whole function to Rn. So just keep the dimensions also in mind. This should be in Rn. The HP is in R, RK, HQI is in Rn. Each HQI is in Rn. So this should somehow make it Rn. Okay. That's another syntactic check, not a semantic check. Okay, so in the interest of time, it's a very simple thing. All you're doing is, see, you want HQIs to be syntactically dominating because you want it to be in Rn. Just take the P ith component of HP. That's what is happening here, right? So you'll have summation of HPI of HQI vectors. Each HQI vector lies in so HPI. Yeah. HPI is a scalar, HQI is a vector. So this is I equals 1 to K. So there are K components in HPI and there are K such HQI n dimensional vectors. So overall this will be in n dimensions. This is clear? Now, does it ring bells? Does it look similar to this? I mean, it looks similar, right? You're just weighing, basically saying weighing the gradient or the vector of partial derivatives of the inner component, right? When you consider FSP of x, Q of x, weighing the inner component with an outer component, its partial derivative. The same form. Is clear? Now it is a subgradient, by the way. It is a subgradient. It turns out to be the gradient when it both are differentiable. But if they're not, then there could be more subgradients as well. We haven't proved that this is the only subgradient because all we showed was this inequality, right? We had two steps in the inequality. We showed the inequality holds, but doesn't mean that this is the only way inequality can hold. Okay. What do you think will happen if you consider the other way, right? So this was when we had P to be a convex, non-decreasing, and Q to be convex. What happens if you consider the other way? P to be convex and non-increasing and Q to be concave. Do you think the expression will change or do you think it will be the same? It will be the same? How many of you feel it will differ? There will be a flip. So if you just run through the same steps, right? What will happen? This inequality, will it flip in sign? Will flip inside, it will flip. This will flip. But what happens after this? Because of concavity, there will be one more flipping. In fact, there will be negative sign once you go the other side because concavity. So eventually you'll get the same expression. So the proof is very similar. So you can clearly see from some differential derivation why this non-increasing goes well with concavity and while non-decreasing goes well with convexity. Okay. Yeah. So this is exactly what I've said. If Qi is concave, P is convex and non-decreasing each argument, you will have to do similar things. Concavity, the sign will flip. Right? QOIY will be less than equal to QIX plus HQI transpose Y minus X. And can similarly write down that a subgradient or a subset of subgradients will turn out to be exactly this summation HPI into HQI. HQI vectors scaled by HPI scalars. This expression will remain. So this expression will remain the same, exactly the same. Okay. Now there are some other interesting cases. We have done 2 or 3. There are other interesting calculus operations as well. And those will also come up quite often. Can I erase this part? So this is very interesting when we talk of projection. The proximal operator. Very, very useful. So we recall that when we were trying to motivate projected descent, many algorithms benefit from projection. In fact, when we were trying to do matrix completion, we again talked about projection. So that relates to the notion of proximal operator. So what are we doing here? So let's say Cxy is convex in xy. And dx is a new function which evaluates the infimum, the lower bound. Infimum, the counterpart of supremum, and you're considering minima, which in the asymptotic case, right? When in the limiting case, sorry. Infimum y in C of C x comma y. With this is with the assumption that C is convex in x and y both. So this is typically when you are looking at distance, want an x, measure the distance of point x from a set C that contains all these y's. So a classic example is when C is the norm, right? So here's an example. Dx comma C that returns the distance of a point x to a convex set, right? So dx comma C is infimum of, let's actually show this pictorially. So you have a set C, dx comma C, the distance of a point x from C. How do you measure this distance? Well, the distance is basically measured in terms of another function C, cxy. In this case, say the Euclidean norm of the distance from x to y. This is an example. Cxy is 2 norm x minus y. So this 2 norm x minus y is a function of two variables x and y. So if cxy happens to be convex in x and y, then d can be shown to be a convex function. The dx comma c is a convex function. Okay. So from this you get the proximal operator. What is proximal operator? It's basically saying let's say a convex function fx exists, then proximal of f at point x is fi plus 1/2 x minus y norm square. Okay. I'll give you a motivation here. So let's say I have to, okay, in fact, we'll go back to Lasso, right? Remember Lasso, what was it case? And we'll in fact show its application very quickly. So Lasso, you had y x minus y norm square plus lambda or 1/2 plus lambda 1 norm of x, right? And what was its subgradient? We had this x plus lambda s. You remember? It's if this is fx. Subdifferential of x is of this form, right? Now you may say, well, this is a little complicated to evaluate. So what proximal operator says is, oh, you have that difficulty. I'll give you an alternative. And that is what we are showing there on the board. So what will we say is, well, let's assume that the second component doesn't exist. Okay, so let's consider the gradient of 1/2 x minus y norm square, which is a very simple x. Sorry? Sorry, x minus y. It's a simple x minus y. So what proximal says is, oh, I am now going to find the new element. I'll compute this x minus y. I'll pretend as if the second component didn't exist. After computing the gradient for the first component, then I'll do a proximal step. So this is the proximal use of proximal operator. This is just use of, okay, motivation for. So first is usual gradient And the second step, you'll do called proximal projection. So you'll say, well, I want a point that minimizes the one norm of x, but is closest to x minus 1. Okay. So, of course, when we say, so let's say prox f of x is argument of this function, right? This function f5 plus 1/2 x minus y norm square. This x minus y norm square is not this norm square. Okay. So I think I'll do the following just to help you. I'll give it a different name. So let's say this is f of y is f simple. F of x is f simple of x. So what I'm referring to as the gradient here, the usual gradient here, is the gradient of f simple of x. And in the second step, the proximal projection, what I do is, that's the prox operator there. So here the prox is computed with respect to the simple function f. Okay, so prox f x is that yeah. Actually, I go to this small prox. Small prox is min over y of f simple x minus okay. So this is an application. You can pay attention to the board here. How will you use prox operator or motivation? Let's not call it use, motivation for. Let's name it motivation. Motivating. So how do you motivate? I'm saying that for this Lasso kind of expression, if I had a simple to differentiate expression plus a not so simple to differentiate expression, then I will, in the first step, compute the gradient of the simple to differentiate expression, give it a name. This is my so-called y, which you see in the slide. This is my y. Okay. Oh, this is my actually fy. This is my fy. So I'll just give it. So there's a little bit of notational overload here. Just call it simple gradient. The proximal projection will say, I want to now come. Since I've decomposed the problem into two parts. In the second part, I'll find a y which is close enough to the gradient of my simplified function. Distance is measured in terms of norm square, Euclidean norm square, plus, well, get me the y which has a good enough one norm. And we'll show the application of this, okay? You'll find it very interesting. But is this clear? I mean, is this motivation clear? This is just the motivation. Okay. The motivation for the so-called prox operation. Compute a simple gradient and then try and find a vector which comes close enough to this gradient and a vector that is also simple in terms of or regularized in terms of the same norm which was there in the objective. And this becomes useful if the simple function had lots of matrices and all that, right? So earlier we said y minus norm x square. That's what we simplified Lasso. We removed the matrix. But if you bring back the matrix, I'll tell you this is going to be very helpful.
This is for finding the subgradient.
No, this is basically a proximal operator. I'm just defining the proximal operator here itself. This is the proximal operator.
So
Prox fx. Sorry? Argmin. This is argmin, no? Not min. This is argmin 1. Yeah, so what did you do with this? We'll actually use it for gradient descent. We'll do proximal gradient descent. This is what gives you the proximal gradient descent. And in the proximal gradient descent, the generalized gradient descent, all of them arise from here. Okay. But what's the motivation again? Please understand the motivation first without getting into the details. I want to break a complex problem into simple parts. One part which is differentiable, one part which is not differentiable, but it's convex. I will blindly take the derivative or gradient of the differentiable part, pretending as if the non-differentiable part did not exist. And then I'll do a proximal operator. This is the proximal projection. Prox f, right? Argument. So this, in this case, prox f is nothing but the prox gradient f simple. So I'm finding a proximal projection into the gradient f simple. Okay. So this is a special case. What's the special case of this? So all this is, I mean, I'm motivated using a one norm, right? So one norm regularizer. What do you think is the special case here? Okay. Yes. But even more special case. That's one special case, but even more special. So that's a silly case, simple case. You're just saying I have two differentiable components. I'll pretend as if only the first one exists, and I'll pretend that is not interesting enough.
Zero there.
Okay, if simple is zero, yeah, that's also those are extreme cases. Yeah, there are multiple special cases. But what is my special case here? Right. So what if I told you that this one norm is replaced with an indicator function? Indicator function saying, well, is your one norm less than one at all, right? Some sanity check, right? So special case is when I'm trying to do an indicator. IC is saying, oh, is my solution in this set C or not, right? The special case is IC of X, which is 1 if X is in C. Oh, sorry, X is 0 if X is in C. It is 0 if X is in C. And basically it is negative infinity. So infinity otherwise. Okay, it's just shooting out. So this one special case, this indicator function obviously is not differentiable. But we are saying even in such a case, I will pretend as if the second component indicator function didn't exist. Find a gradient and then do a projection onto the set C. So instead of doing a projection, so this is called proximal projection, but there's a proximal operator. But there is another one which I'm showing on the board, right? Special case. You can't see this right here. Special case. It's called projection. Projection. And what am I doing here? I'm saying argument over y of whatever the simple function I had got, f simple, x minus c. But instead of saying lambda times one norm of y, I'm saying argument over y in C. So I have a C set here. I want a y here, which is close enough to the gradient of the f simple. So f simple might have gone out. I want to project it back. You remember I said that's one of the simplest things, projection. I go outside a set, I draw a perpendicular and into the set and say project you back. You go out, right? Project it back. If one of the components goes greater than 0, I clip it to 0. That's one kind of projection. Very intuitive. But that's also resulting from this so-called proximal operator. Is this clear? So that's what I've illustrated here, right? You've gone, X has gone outside. I'm just pulling it back to C. That's a special case. Right? So 60 is an open convex set. It becomes even more interesting. Here you see this example. The C is open. Open, deliberately I have put dotted line outside. Right? So the minimum is not even defined. So what will you do? You'll use an infimum. So why infimum? Because C may be open. Therefore, infimum makes sense. So infimum of x minus y norm square. So I hope everything in this slide has made some intuitive sense. We'll see more of this. Right? This is our first brush with this proximal.
Does the projection become troublesome in the case of an open set?
Yeah, with open sets, projections can be tricky. But what else can you do? Right? I mean,
You can't find a point you will the top.
you can do it iteratively. You can take the closure of the set and hope that the point lies in the set. Right? In fact, unless the function is pathological, even the closure does work well. Okay, so this is the now how do you compute the subdifferentials? All this was a special case. All this was a proximal thing. Now what does the subdifferential look like? The subdifferential is basically it depends, right? If it's a prox, okay, so for the prox, the subdifferential so there we have written the slide is written in terms of f, but it is the same thing. So sorry. Yeah. So in this case, it is the subdifferential of y, one norm of y, right? Plus grade of central minus 1. Or the other way, sorry, y minus. This is the prox, right, for the one norm function. But you replace the one norm function with some other function, you will consider it subdifferential. Plus y minus that simple gradient that I computed. Okay, I'm not just copying what is there on the board, I'm giving a special case on, trying to realize it with respect to something you know on the board. Likewise, if you look at this special case of projection, what will be its subdifferential? Well, the subdifferential of the, so I won't write it here, it's a little tricky and we won't use that much. But the projection, you know how you would do, right? You just compute the shortest distance. But the subdifferential of that happens to be something called the normal cone. NC is the normal cone to the C. In case you recall from the supporting hyperplane, right? So H is in Rn such that H transpose Y is greater than or equal to H transpose Z for all Z and C. So it should be lying on one side. The set C should be lying on one side. That's what gives you the supporting, that's what gives you the normal cone Y, normal cone H. Okay. So some of this is little advanced and optional. I'm going to run through all of this. Okay. So perspective functions. Again, this is a special case. So we have considered 3 cases so far. Third was proximal. But we'll see proximal again. Okay. So don't worry about it. The fourth is perspective. So if I were to look at the screen from here, right? Or maybe from here, I have a perspective transformation. What is a perspective transformation here? In fact, I think I have a figure here. let's say this sentence here is good morning, right? So when I'm looking at that from a side, then there's a transformation in terms of both t and x, right? So, so the transformation is basically that I'm scaling it by rescaling it by t, right? You see this rescaling the argument or dividing it by t, applying f, and then scaling it again by t. So the text there is shrinking. I apply to a transformation because there may be a lens, and then I post multiply by t. So this, in case the perspective transformation is there, I mean, there are some interesting transformations. For example, for minus log x, the perspective transformation is the cross entropy, relative entropy function, right? So what does this mean? This is called cross entropy. We have used cross entropy is used extensively in classification. So it's a perspective transformation of negative logarithmic. So log or negative logarithmic operators you'll find often when you look at likelihood, right? But you're trying to say maximize the likelihood of some observation. Perspective transformation is saying, well, I have the likelihood, but if I were to view that from the perspective, right? So I'm trying to maximize likelihood what? Parameters. I have some parameters that yield the best posterior distribution on the data set. Oh, sorry, the distribution on the data, right? In the case of cross entropy, I'm trying to match the distribution with respect to the empirical distribution. The data distribution and the empirical distribution you're trying to match. So there's a perspective that the empirical distribution is bringing in. Okay, so maybe in the next few minutes, I'll just finish this subgradient kind of function. So far we are looking at subgradients of functions, but subgradients themselves are functions, right? That's the reason in many places we put HPX, right? Evaluated at X. So subgradients are also functions. Gradients are also functions. So what do you know about these subgradient functions? This is again, little, as I said, not too critical. Good to get an intuition. So a differentiable function is convex if and only if f dash is increasing or strictly increasing if it's strictly convex, right? So if it's convex, then f dash should be increasing. Can the same hold for subgradients? Is there close an analog for vector valued functions as well, right? So can we use subgradients as an instance of a general function from D to Rn, and D is a subset of Rn. Okay, so yes, a subgradient kind of function H is monotone if the dot product of difference of the function on two points x1 and x2 with respect to the difference of x1 and x2 is greater than equal to 0. Yes. So the only problem is we can't talk of first order. The function is not differentiable. Yet does the subdifferential give me some similar intuition? Right? So yes, you would expect the subgradient obviously subgradient exists for convex functions. You would expect the subgradient to have some kind of monotone property. Now, is this asking for too much? Because this is saying that for any x1 minus x2, for any x1 comma x2, h of x1 minus x2, this should make basically an acute angle with x1 minus x2. Take 2 points, x1 and x2, x1 minus x2 and h of x1 minus h of x2. They should basically form an acute angle. They should be similarly oriented. right? Think about it, right? Think if this has, is this over? We are not saying component wise. We are not saying the component wise each element of H has to increase. Right? That's what would happen in F, right? If F is convex, yeah, F is convex, if and only F dash is increasing. Here we are not saying that each component has to increase, but we are saying, well, the the H x1 minus H x2, basically the difference of the two subgradients should be in the same direction. Sorry, yeah, should be the same direction as the difference of the two vectors. So that's one. I'll just run through these properties and leave. We'll pause for today. There's, like we talked about monotone, this notion of strict monotone, like strict convexity, strict monotone. Strictly monotone just means that they will make a strict acute angle, cannot be collapsing. Also cannot be orthogonal. Sorry. It cannot become zero. The dot product cannot become zero. And the third is there's a notion of strong monotonicity, that the dot product is lower bounded by some quadratic function of the norm of the distances, the distance of the x1 and x2. Okay. So I'm going to leave you with this last relationship and we'll continue next time. This is going to be useful for just you to think about. So we are saying F is convex if and only its gradient is monotone. So now we have talked about the first order conditions for convexity. We are saying that if the function is convex and differentiable, which means its gradient exists, then the gradient must be monotone, and it's a necessary and sufficient condition. Strictly convex means the subgradient should be strictly monotone, and strongly convex, the gradient is strongly monotone. So I'm going to leave you the question. All this is fine if the function is differentiable. What if the function is not differentiable? So can I say that the function f, even if it's not convex, I repeat, right? I just removed, sorry, not differentiable. A convex function f, even if not differentiable, is guaranteed to have a subgradient. Can I say that the function f is convex, even if not differentiable, if and only its subgradient, every subgradient f is monotone? It is strictly convex if and only every subgradient of f is strictly monotone, and yeah, strongly convex if and only every subgradient is strongly monotone. Okay, so I drop differentiable and replace gradient with subgradient. Does this hold? Please think about it. I'll leave you with this homework problem. Okay. Is this problem clear?
There's some lag in
Sorry?
But you're saying every subgradient. Just one very special subgradient.
If it holds for that. So are we not done? Can we be done? Good question. So his question is, why should we talk about every subgradient? Why can't we relax and say some subgradient?
Bounded by like the extremities.
So our argument seems to be that you may be able to get the others as convex hulls of some of the subgradients, like we saw in the case of max of multiple convex functions. The subgradients were all like convex hulls, right, or closures of the convex hull. Think about it here. I don't think we'll delve too much into it, but so I've made a note here, right? While these results also hold for some more advanced proximal subgradients. Okay, so these do hold for some notion of proximal subgradients. Not always, as he pointed out, it doesn't hold it doesn't have to always hold, but does hold in some restricted settings. So I've given a hint there. But in the slides, what I'll do is I'll leave you with the proofs. This proof is not going to be covered in the class, so you must do these proofs by yourself. Write the proof for all these conditions. Necessity to show that for the differentiable case. This is very simple, right? I mean, it's too boring to do all of this in the class. So this is necessary condition is to show that if it's, in fact, I start with strong convexity. So if it's strongly convex, then show that the gradient is strongly monotone. Sufficiency for the same, right? And the basic idea is this, right? So if you have, um, you know the mean value theorem, right? So the existence of some point between the two where the slope approximates or slope is exactly the same of the as the slope of the graph, right? When you use that, you're able to actually show the sufficiency condition. Okay, so yeah, I'm just going to leave you with that. So I want to start with minimization next time. Okay, so I'm going to leave this reading also as homework. So what you should do is try and look at this and imagine, right? If you replace these gradients with subgradients, what would happen? Where would it fail? So it's okay to say it does. I don't find it going anywhere. But where does it break? Where does the reasoning break? Does a mean value theorem break? That could be one place. I don't find a mean value theorem applicable when function is not differentiable. Right? So think about this. I'll leave it at this point. Thanks.